Today's episode dives into three very different but deeply connected frontiers of AI: how spiking transformers can finally bridge the gap between elegant theory and practical efficiency, why vision language models still struggle to truly reason over images, and when early exit networks can generalize better by adapting their depth on the fly. From effective dimension and spike counts to modality gaps and PAC-Bayesian guarantees, these papers reveal both the hidden limits and the surprising strengths of modern neural systems. Let's explore the first paper, Closing the Theory-Practice Gap in Spiking Transformers via Effective Dimension. Closing the theory-practice gap in spiking transformers via effective dimension gives the first expressivity theory for spiking self-attention with leaky integrate and fire neurons. It proves universal approximation of continuous permutation equivariant functions and supplies explicit spike circuit constructions, including a novel lateral inhibition winner-take-all module for softmax normalization with O1 square root T convergence. The paper also derives an information theoretic spike lower bound. Epsilon approximation requires omega, L, F squared, and D, epsilon squared, total spikes, and extends this to input-dependent bounds using effective dimension, def, rather than ambient dimension, ND. That effective dimension analysis is the key novelty. Empirical PCA on training data yields def equals 47 plus or minus 3 for CFAR, 10, 68 plus or minus 4 for CFAR, 100, 89 plus or minus 7 for ImageNet, 1K, and 52 plus or minus 5 for SST2, explaining why practical models succeed at t equals 4 to 6 time steps, even though worst-case theory based on ND equals 3072 or 150,528 predicts t is greater than or equal to 10,000, a 45 1,691 times gap. A calibrated design rule emerges. T is approximately equal to 2.3 def epsilon squared, with 95% CI 1.9, 2.7. Experiments on spike former, QK former, spiking Reese former, and spiking BERT validate the theory with R squared equals 0.97 and P is less than 0.001, and observed spike error scaling follows the predicted epsilon is proportional to 1 square root n total law with slope 0.48 plus or minus 0.03. On ImageNet, 1K, spiking transformers retain 74.885.7% accuracy while using 3857 times less energy than Vite B. 16. The framework also characterizes bounded spiking attention as TC0, implying constant depth computational limits unless spike count scales with input size. Let's explore the second paper. Do vision language models truly perform vision reasoning, a rigorous study of the modality gap? The paper argues that current VLM vision reasoning is largely text backbone reasoning with visual inputs as a net liability. Its core contribution is cross-math, a strictly aligned benchmark of 250 human-verified evaluation puzzles and 5,000 training puzzles, each rendered in text-only, image-only, and image plus text forms with identical task-relevant information. The puzzles are 2D cross-arithmetic grids requiring multi-hop symbolic deduction. The authors also extract stepwise gold reasoning paths and stratify difficulty by hop count, enabling micro-accuracy, macro-accuracy, and K-hop evaluation. Across Quen 3, 5, and Quen 3, 6 VLMs, the modality gap is extreme. Quen 3, 5, plus reaches 92.8% macro accuracy on text only, but only 12.4% on image only, while image plus text often underperforms text only. For example, 74.8% versus 92.8% macro for the same model. This pattern holds broadly, with image-only performance around 3.2%, 16% macro for zero-shot Quen 3, 5 variants. The gap is attributed less to OCR, perception failure, than to weak visual-to-symbolic reasoning and poor maintenance of multi-step dependency chains, supported by sharp accuracy collapse as hop depth increases. Post-training on cross-math mitigates the deficit. On Quen 3, 59B, supervised fine-tuning raises image-only macro accuracy from 3.2% to 48.5%, and adding GRPO improves it further to 50.4%, while text-only also rises from 44% to 76.4% macro. These gains transfer to out-of-domain math benchmarks. improving MathFirst from 48.94 to 51.4 and MMMU from 67.52 to 68.91. The paper's main claim is that closing the modality gap requires stronger visual grounding and reasoning-oriented post-training, not just larger language backbones. Let's explore the third paper. When do early exit networks generalize a PAC-Bayesian theory of adaptive depth? This paper gives the first PAC-Bayesian generalization theory for early exit and adaptive depth networks, replacing worst-case depth, K, with the exit depth distribution. The central result is a bound of the form E, Q, L, P, F, P, L, E, Q, hat, L, S, F, P, plus CQRT, mathrm, KL, Q, P, plus E, Q, H, D, plus line, iki, CQRT, N, delta, ikin, where HD is the entropy of the exit depth random variable. For deterministic threshold policies, this reduces to a closed form with HD only. This yields sample complexity, OED, C.D, plus HD, epsilon 2, versus the fixed step scaling, OKD, epsilon 2, and the authors derive an explicit leading constant, 2 ln2 approx 1.177. They also prove depth-weighted Rademacher bounds under progressive refinement, an advantage theorem showing strictly better generalization when easy inputs exit at depth K, E is less than K, and an epsilon approximate extension for learned routing with an added O epsilon K penalty. Empirically, they evaluate 6 architectures: MSDNet, ResNet, 5.6, EE, EfficientNet, B0, EE, BERT plus PABI, DistilBERT, and GPT-2 plus Calm on 7 benchmarks, including CFAR, 10, 100, ImageNet, 100, SST, 2, MRPC, QNLI, and Wikitext2. Their bounds are much tighter than classical VC or depth-agnostic PAC-Bayes, with reported tightness ratios of 1.5 to 3.87 times, while classical bounds exceed 100% or 613 times. Generalization gap correlates strongly with exit entropy. R equals 0.96, with P is less than 0.001. Bound-guided threshold selection matches validation-tuned thresholds within 0.1–0.3%, reducing the need for held-out tuning in low-label or privacy-constrained settings. That's a wrap on today's AI paper highlights. Thanks for watching.